welcome back students. In the last lecture we studied the boundary conditions in general, and we saw what the kinematic boundary condition means. We derived an equation of the general surface and the kinematic boundary condition related to that surface. In this lecture we proceed forward with the bottom boundary conditions, also called as BBC. So, let us say the bottom is described as z is equal to minus h of x. So, if there is, this is the river bed or the sea bed, and this can be z here. So, if this is x and this is z, right. So, this depth z is equal to minus h of x, because we are considering the 0 at the free surface, if we consider 0 at the free surface. All right. So, here origin is located at still water level, that is the surface of the water. So, again drawing, this is the origin, let us say this is this. All right. Since from the boundary condition we see the bottom is fixed, so u dot n is going to be 0, all right, which we have seen in the previous lecture. So, we can write the surface equation as, so the equation was z is equal to minus h of x. So, we can write z plus h of x is equal to 0, and we call it as f function of x and z, all right. And u dot n is equal to 0. If we assume u is a combination of small u I plus w k, so this is the velocity vector. This is a general u that we can assume in 2 dimension, x and z. So, we are going to apply what we have learnt in the previous lecture. So, delta f is going to be delta f del x plus delta f del z. This is in I direction, this is in k direction, all right. And instead of this f, we put z plus h x. So, what we get is delta del x of z plus h x here I cap plus del z plus h x at k cap, all right. So, delta f will be del h del x I cap plus k cap, this will be delta f, all right. So, n will be delta f divided by modulus of delta f. So, we will get dh dx I cap plus k divided by 1 plus dh dx whole square, simple mathematics. So, and u dot n, u if we substitute u I cap plus w k cap, and n we already know this was n, right. So, if we do dot product of u dot n, what we get? We get this multiplied by this multiplied by this. So, we get u dh u dh dx plus w is equal, because here whatever is there 1 plus d delta h delta x whole square is equal to 0. Therefore, if it goes this side, we get u dh dx plus w is equal to 0. This is u velocity and this is w velocity. U velocity means x direction, w means z direction. So, we get u dot n is equal to u dh dx plus w is equal to 0 on the surface, or we can simply write, if we use this equation, we write w is equal to minus u dh dx on the bottom boundary. Now, earlier we had assumed that the bottom, I mean z will be minus h of x, all right. But if we assume a case of horizontal bottom, in horizontal bottom we know that the height will not vary as a function of x. So, dh dx is going to be 0 for horizontal bottom, which we have written here. Therefore, this means w is equal to 0. So, we have now proved at the boundary w is equal to 0 using the bottom boundary condition, and we have derived everything from the basics of the boundary condition. Now, if we have a sloping bottom, we can simply write, in case of a sloping bottom like this, we can write w by u is equal to minus dh dx. Very simple. The question to you is, could we treat this bottom as a streamline or not? Yes, since the flow is everywhere tangential to it. So, this bottom can be treated as a streamline because w is equal to 0 and therefore, the flow is everywhere tangential to it. So, the bottom boundary condition, which was equation number 7, also applies to flows in 3D in which h is h of x comma y. You remember we started derivation with z is equal to minus h of x, but let us say z is not only a function of h of, but it is also a function of x and y, then also that bottom boundary condition equation 7 will apply. Just it will have one more term in the differential equation that we have. So, another term is kinematic free surface. See, first we studied the boundary condition, we studied kinematic boundary condition in detail. So, the first sub part of that was we saw the bottom boundary condition where the boundary was fixed, where we utilize u dot n is equal to 0. Now, there is something called kinematic free surface boundary condition. Free surface means, free surface of water is written as, so if the surface is free, it can distort, if you recall from our open channel flow lectures, right. So, if the surface is something like this, then the free surface, and this is eta as a function of x, y and t, then we can write f of x, y, z comma t is equal to z minus eta x, y, t. So, here eta x, y, t is the displacement of free surface about horizontal plane, z is equal to 0, this is z is equal to 0, all right. So, delta f, so we are going to apply the same conditions, the kinematic boundary conditions. So, we start calculating delta f because we already have an equation f here. So, first step is always calculating delta f. So, delta f is going to be delta f delta x I cap plus delta f delta y j cap plus delta f delta z k cap, all right. So, if we put f as here z minus eta x y t, then we get minus del eta del x minus del eta del y plus k kappa. So, minus del eta del x I cap minus del eta del y j cap plus kappa k cap. So, because it will be 1 dot k cap because we had the term z here. you see, alone term z, and delta f is going to be, if we take the modulus, it will be 1 plus delta x so modulus is taken from here, this term, delta eta by delta x whole square plus delta eta by delta y whole square, and the unit normal vector will be delta f by modulus of delta f. If we assume this velocity is 3-dimensional, ui, vj and wk, then u dot n is going to be minus u del eta del x minus v del eta del y plus w. So, u is ui plus vj plus wk, and eta is minus del n cap is del eta del x I cap minus del eta del y j cap plus k cap. If you do u dot n is equal to 0, so if you see I and I will become minus u del eta del x plus minus of v del eta del y plus w, or divided by, of course, the denominator, okay, 1 plus del eta del x whole square plus del eta del y whole square. So, u dot n is going to be minus u del eta del x minus v del eta del y plus w divided by the denominator. Okay, same as this one here. So, this is what we get, u dot n. Now, if we use equation 6, equation 6 was this, all right. So, this is u dot n, and if we do del f del t, it will be del eta del t divided by modulus of f. This and this will get cancelled out. So, we will get w is equal to del eta del t plus u del eta del x plus v del eta del y at z is equal to eta of x y t, that is at the free surface. This is the equation of the free surface. This is an important equation. All right. So, this is the kinematic free surface boundary condition. All right. So, there is another boundary condition called dynamic free surface boundary condition. So, boundary condition for fixed surfaces are easy to prescribe as they are applied to the known surface. All right. However, the displacement of the upper boundary in free surface problem is not known. We do not know from before how much that the free surface will go above, right, because I mean the bottom is fine because it is fixed, but the displacement of the free surface is not known from before. All right. So, that is one of the problem in the wave problem, in water wave problem. Second thing is that the fixed surface are able to support pressure variations across the interface, whereas free surface cannot support the pressure variations, it will distort. Okay. Therefore, another boundary conditions is required for any free surface or interface to prescribe the pressure distribution on the boundary. Since the free surface cannot support the pressure variation, we need to prescribe another boundary condition to tell what the pressure distribution on that particular boundary is, and this is called the dynamic boundary condition. So, you see we started from the boundary conditions, we went to the kinematic boundary condition where we saw the bottom boundary condition and kinematic free surface boundary condition. But one typical thing with free surfaces are they cannot support pressure variations across it, unlike the fixed surface. Therefore, another boundary condition or another boundary condition is required, that is called the dynamic boundary condition. Dynamic free surface boundary condition requires that the requirement of the dynamic free surface boundary condition is that pressure on the free surface be uniform along the waveform. So, along that free surface distortion or wave as we call it, the requirement is that the pressure on the free surface should be uniform along the waveform. And here to derive that we use unsteady Bernoulli's equation on the free surface. So, we have seen the Bernoulli's equation. For this we are going to use unsteady Bernoulli's equation. Unsteady means there is going to be another term with del t. So, you remember this was a typical Bernoulli's equation. To make it unsteady, we add another term, this is unsteady part. All right. So, to derive the dynamic free surface boundary condition, we make use of the unsteady Bernoulli's equation. Here rho n is constant and usually taken as gauge pressure, that is 0, atmospheric pressure, but we take it P n is equal to 0. Now, if there is a wavelength of if wavelength are very short, that the surface is no longer free, you have to write the dynamic free surface boundary condition for this case, where surface tension T is important. All right. So, to be able to do that, I will solve the dynamic free surface boundary condition in this case. Consider a surface for which the curvature exists and is as shown below here. All right. So, this is T, and this is alpha, and the gauge pressure is P n, and we have considered this distance delta x. All right. So, if we denote P as the pressure under the free surface and a free body analysis in vertical direction. So, we have to do the free body analysis in the vertical direction. So, this is the direction, vertical direction, V direction. So, we can write T minus sine alpha, okay, because this will a component here, and sine alpha plus sine alpha at this point, because this is negative, this will be positive, plus because of this pressure difference P minus P n into delta x plus different terms of delta x square. All right. So, here we assume that delta eta by delta x is equal to sine alpha. All right. How? You see, this is, so this will be, at this point there will be eta and there will be point eta. So, the difference between them del eta by del x will be sine alpha. All right. Or we can take this one also as delta x, because we are considering very small. So, here we take delta eta by delta x is equal to sine alpha. So, if we expand it using the Taylor series and allow delta x going to 0, we will get P is equal to P n minus sigma dash is nothing but T del square eta by del x square. All right. If you put sine del eta del x at sine alpha, this is what we are going to get. So, therefore, the dynamic free surface boundary condition becomes, so what we have done, we have just prescribed P n, you see P total pressure, Therefore, it becomes Pn by rho minus, so instead of P here in the dynamic free surface boundary condition, we put the pressure here and rest of the things remains same. You see? So, this is u square, this is v square plus P by rho, so that becomes Pn by rho minus sigma dash or T by rho into del square eta by del x square plus Gz is equal to C of T. Okay, this was a very simple example. You must have prior knowledge of the surface tension from before to be able to do that, how to apply this problem, but this is just a way of showing the dynamic free surface boundary condition. Now, another boundary condition, that is called lateral boundary condition. Until now we have discussed the boundary condition for bottom and upper surfaces, right. So, bottom boundary condition, at the top we have discussed about kinematic free surface boundary condition and dynamic free surface boundary condition, but there are many other surfaces, right. This is also one of the boundary. So, these we must also specify the remaining lateral boundary conditions. So, let us say one of the conditions could be if waves are propagating in x direction. That means, by the sentence itself, this means there is no flow in y direction. Therefore, the no flow in y direction is one lateral boundary condition. In x direction, if motion occurs due to a paddle or the wave maker, then we can apply the usual kinematic boundary condition, all right, on the side. Okay. So, the waves are being generated here, right. So, due to a paddle here. So, the boundary condition at this surface we can apply similar to like the kinematic boundary condition, no changes. So, consider a vertical paddle if the displacement of the paddle is described as x is a function of s, z, comma t. The question is find the kinematic boundary condition. So, this is x is a function of z, comma t. Okay, this is the paddle. So, the movement is in x direction of the paddle, right. Therefore, we say x is equal to a function of z, comma t, s function z, comma t. All right. So, with this surface equation x minus s z comma t is equal to 0 or f, you can use the similar analysis of the kinematic boundary condition. You remember u dot n is equal to minus del f del t by mod delta f, all right. The same thing you will get. Another lateral boundary condition could be for the waves that are periodic. Periodic means they have a wave period and it repeats in space and time. So, for the waves that are periodic in space and time, the boundary condition can be simply represented as phi of x comma t will be same as x plus L, where L is the wavelength. This is periodic boundary condition in space. The other could be, it will be same as at t plus delta t. So, this capital T is wave period. You would get to know what wavelength and wave period are soon, but to complete this boundary condition description, I think this is quite an important thing. Now, after reading the boundary condition, we are getting straight to the derivation of the velocity potential. To derive the velocity potential, there are some assumptions. We started this chapter, this module by saying that it is an inviscid flow. So, following are the assumptions of deriving the expression for the velocity potential phi that has much to do with the hydraulic engineering or fluid mechanics, and it could be due to anything. In our current case, that are due to the propagating ocean waves, are that the flow is irrotational, all right. Fluid is ideal, surface tension is also neglected, and the pressure at free surface is uniform and constant. Also the seabed is rigid, horizontal and impermeable. These are some of the top 5 condition, and this ideal in viscid flow. Total ideal conditions we have assumed. All right. Now we also assume some additional conditions, that wave height is small compared to the length. So we see, yes, you see, so this is, let us say, amplitude is equal to wave height by 2, but this wavelength lambda, I mean this is lambda by 2. So we say this lambda by 2 is much larger than h by 2. Okay, this is not a very good representation, but just to let you know that we for this derivation we have assumed wave height is small compared to its length. We will come to it why. The potential flow theory is applicable because we have assumed the ideal fluid. Therefore, under the ideal conditions like this, a velocity potential phi exists, and the velocity component u and w in the x and z directions can be obtained as del phi del x and del phi del z. So, we have assumed that the flow is occurring in two directions, x and z. Therefore, there will be only two velocity components, u and w, and if we know phi, we can obtain u as del phi del x and w as del phi del z. All right. So, the governing equation, so we go back and remember what we learned in the Laplace equation. The Laplace equation was, we go back and listen to, try to remember the boundary conditions. There we said first we establish a region of interest, that we have already done, ocean surface waves, or oceans are the region of interest. Now we must find a equation that should be satisfied because of the assumptions we have taken. In the current scenario, we can assume that Laplace equation is that governing equation which will be satisfied. So, Laplace equation for phi can be written as del square phi is equal to 0 for our current case. All right. The continuity equation and the Bernoulli's equation are used in the solution procedure. So, this is the continuity equation, del u del x plus del v del y plus del w del z is equal to 0, and also the unsteady Bernoulli's equation for the boundary condition. You remember the dynamic free surface boundary condition. So, these are the three equations that are used for the solution procedure. All right. Now, the boundary conditions, equation 2.1, this Laplace equation is to be satisfied from the water depth. If we say the water depth is minus d to the free surface of the wave. So, try to, you see, so origin is at free surface. So, this should be satisfied, this is eta and this is, so z should be satisfied from minus d to eta. All right, and we have considered the entire ocean. So, x will be minus infinity to plus infinity. Here eta is the water surface elevation measured from still water level. If this is a still water level, so this is eta, because below is the depth, here is the eta. Eta is the water surface elevation measured from still water level. This is SWL. All right. The kinematic boundary condition, meaning that the vertical velocity component at the sea bottom is 0, right, because at the sea bottom we have already seen that W should be 0. This is one of the condition, and the pressure at free surface is 0, atmospheric pressure, but we have assumed it to be gauge pressure, Pn is equal to 0 at Z is equal to eta. These are the boundary conditions. Now, if we linearize the Bernoulli's equation, So, linearizing means taking out the second order term. So, we take out u square plus w square, alright, because those are quite small at the free surface. So, this is the linearized boundary condition that we linearized Bernoulli's equation that we get. So, when the height will be z is equal to eta, that means at free surface if we take p is equal to 0, equation 2.4 we are going to get eta is equal to 1 by g del phi del t at z is equal to eta. So, in terms of velocity potential we have obtained by linearizing the Bernoulli's equation, we have obtained, you see why we have assumed u square plus w square is equal to 0. You see at the top there will be no velocity of the fluid particle, that is why it is going down under the influence of gravity, that is why half u square plus w square is going to 0, alright, and that is why we were able to linearize and avoid this term in here. Okay. So, this is the eta is equal to, so eta which was unknown from before, using the dynamic free surface boundary condition, this dynamic free surface boundary condition, we have been able to write eta as a function of velocity potential. You see how important that tool was, alright. So, this is the dynamic free surface boundary condition. Since we assume that the amplitude of the wave are small, see one assumption was that the amplitude of the waves is very small. So, this eta actually is very small, alright. So, we can also write, so this is a problem if we say z is equal to eta, because we do not know eta from before, this becomes implicit equation, right. So, with this assumption of that the waves being small, this eta can be written as, instead of z is equal to eta we write z is equal to 0, because eta is very small, alright. So, it will be z is equal to 0. Now, you see this is an explicit equation in eta of eta, where if we know the velocity potential we will be able to find and found by assumption of small amplitude. So, this has been found out by assumption of a small amplitude, alright. So, this is applicable only when eta is small and valid for these condition which you do not have to worry about it now. So, I will show you the definition sketch. So, just describing, see this is the sea bed, z is equal to minus d, this is still water level, z is 0 at this line, alright. So, this is the depth minus d. So, this is the half of wave height or amplitude, the full wave height will be between the crest and trough, whatever the height is. Wavelength will be from this point to this point, alright. So, I think this is a nice point to stop before we meet again for the next lecture, where we start again by describing very basic properties of this basic sketch of the wave motion. Okay, thank you so much. See you in the next lecture.